SwayamPrabha. Digital India. Educated India.
Hello, welcome to lecture 22, which is continuation of the previous lecture. We are going to study how to find out the shear stress or the shear flow in a thin walled cross section due to applied shear force. So, we are analyzing a beam with a thin wall cross section, and in shear force Sx and Sy are acting on the beam in x and y direction. We are trying to find out what will be the shear stress or shear flow in the cross section. So, in the last lecture we have derived this equation, and from this equation we have found out that by using the expression of sigma z and saying that sigma del sigma z by del sigma z and substituting del moment by del z as the corresponding shear forces, we have derived this expression. Now, in order to find out the shear flow from equation 2, we can say that from equation 2 we get that if we integrate between 0 to s, we get this as minus So, by integrating this we get this equation in integral form. Now, this one can actually be written as Qs minus Q0. So, the integral on the left hand side can be just written as the shear flow at any arbitrary coordinate s minus the shear flow at the origin point, which is Q0. Now, this equation can be utilized to find out the shear flow in a given cross section. So, from the information about the shear forces Xx and Sy and the sectional property of the cross section. So, let me just explain through figure what we are trying to find out. So, if this is a beam, if this is a beam with the shear forces Sx and Sy acting along s and y direction, x and y direction, and if we take an arbitrary cross section of the beam and the cross section is a thin wall cross section. The thin wall cross section can be anything. It can be a C section or any other section. So, S is the coordinate that we have considered. So, if we are starting from 0, so if this is 0, this is 1, this is 2 and this is 3, the 4 crucial point, then we can find out QS at any arbitrary point if from the, so this can be obtained from equation 3. So, this is what we are trying to find out. So, unlike the torsional problem where also we evaluated the shear flow because of an applied torque, but the essential difference between that shear flow and this shear flow is that for torsional problem the shear flow was constant between any two junctions. However, when the shear flow arises due to the applied shear forces, the shear flow varies with the along the cross section, along the coordinate S. So, that is the essential difference between the shear flow produced by a torsional moment and the shear flow produced by a shear force Sx and Sy. Now, with this, let us now do an example and see how this equation can be implemented for a given problem. So, let us consider that we have a antisymmetric jet cross section. So, we have an antisymmetric jet cross section. As explained before, I am drawing the center line of the cross section. So, this distance, this length is h by 2, this length is also h by 2. And this distance is h. So, let this be the x axis and let this be the y axis. Now, a shear force Sy, a shear force Sy is being applied along the y direction. So, the problem statement says that find the distribution of shear flow in the cross section. Now, from equation 3 we have found out, so we need to find out the shear flow, that is QS in this cross section. So, let us name the ends of this cross section. So, this 1, 2, 3 and 4. Now, let us rewrite equation 3. So, from equation 3 I get QS minus Q0 is going to be minus So, this is equation 3. Now, for the given problem or the given example, Sx is equal to 0 and Sy is not equal to 0. So, Sx goes to 0. So, if this is the case, then this can be simplified as Qs minus Q0 is going to be Sy Now, to evaluate this expression, so we have to find out Ixx, Iyy and Ixy. Now, Ixx of this cross section is going to be h cube t by 3 and this one Iyy will be h cube t by 12 and Ixy will be h cube t by 8. Now, if these expressions are substituted in this value in this expression, then we get Qs minus Q0 to be equal to Sy. If we substitute and simplify the expression, we will get this as Sy by h cube 0 to s 10.32 x minus 6.84 y into ds. So, this is the expression that we will get by substituting the values of Ixx, Iyy and Ixx into the above expression. Now, therefore, what we need to do next is to evaluate Qs and Qs for each portion of this cross section, that is portion 1 2, portion 2 3 and portion 3 4. So, let us start by finding it out. So, let us first consider 1 2. So, for flange 1 2, so we will start s is equal to 0 here and s is equal to h by 2 here. So, we have taken this direction to be the positive direction of s, small s. So, if we consider this, then for flange 1 2, s is going to vary between h by 2 and 0. So, s is going to vary between h by 2 and 0 and y can be written as, for the flange 1 2, y is always equal to minus h by 2 and x is always going to be equal to minus h by 2 plus s, because when s is equal to 0, x is minus h by 2. So, this is the origin, the centroid as well. So, when s is equal to 0, that is at point 1, x is equal to minus h by 2, and when s is equal to h by 2 at point 2, x is equal to 0. So, therefore, this is the correct representation of x and y in terms of s. Now, we can say that Q12, which will be a function of x of course, but I have put the subscript 1 2 to denote that we are finding out the shear flow only in the flange 1 2. Now, Q0 is going to be Q1. and that is going to be S capital Sy by h cube into 0 to S. Now 10.32 into minus h by 2 plus S minus 6.84 into h by 2 into ds. So, this is what we have. Now, let us see what is Q1. So, Q1 is at the open end of the cross section. So, Q1 is here, we are measuring Q1 here. So, which is at the open end of the cross section. So, according to our boundary condition, which is on the beam surface. So, according to our boundary condition, all the beam surfaces are stress free. So, Q1 therefore has to be equal to 0. Therefore, this equation can be written as Q1 to S is going to be Sy by h cube into, if we calculate the integral, this integral will be 5.16 S square minus 1.74 Hs. So, this is the expression of Q1 to S in terms of S and H. Now, from this expression, I can find out Q2, which is basically Q1 2 at S equal to h by 2, and that is going to be, if I substitute S equals to h by 2 in this equation, we get Q2 to be equal to 0.42 Sy by h cube. So, this is Q2. Therefore, we have got the distribution of Qs in the flange Q12 by using this expression. So, let me call this as equation 4. Now, if we use equation 4 and try to plot the distribution of the shear flow in the cross section. So, let me draw the cross section once more. If I draw the cross section, then the shear flow here is going to look like so this is going to be Q12S with this value being 0.42 Sy by h cube, and this line is given by Sy is given by equation 4. This line is given by equation 4. So, this is how we can find out the shear flow distribution in the flange 1, 2. Now, let us move into the next part. So, let us now try to find out the shear flow in the portion in the web 2, 3. So, let us try to find out the shear flow. So, we have known from earlier expression that for this particular cross section Qs, I am just rewriting this, or Q as a function of x minus Q0 is going to be Sy. So, this we have derived earlier and we have used it for flange 1, 2. Now, for web 2, 3, how are we going to apply it? So, for web 2, 3, my S is going to start here and it is going to move in this direction. So, this is S. So, this is S equal to 0 and this is S equals to H. So, therefore, for web 2, 3, my S is going to lie between H and 0. And similarly to what we have done earlier, I can write Y as, so Y for web 2, 3 can actually be written as so Y can be written as minus H by 2 plus S, because when S is equal to 0, Y is minus H by 2. So, when S is equal to 0, Y is minus H by 2, and when S is equal to H, Y is equal to H by 2. So, this criteria is satisfied, and then the next thing that we have is x equal to 0. So, x is 0 in this case. So, therefore, we can write as Q23 in of S minus Q0 is going to be Sy by H cube 0 to S 10.32 Now, what is Q0 here? So, Q0 or Q of 0. So, Q0 is this point for web 2, 3. Now, Q0 is basically Q2. So, therefore, this is basically Q2, which we have found earlier to be 0.42 Sy by H cube. Therefore, we can say that Q23S is going to be Sy by H cube 0 to S 10.32 minus H by 2 plus S ds minus plus 0.42 Sy by H cube. Now, we can evaluate this integral, and if we evaluate this integral, we will see that the solution is Sy by H cube into 5.16 S square minus 5.16 Hs plus 0.42 Sy by H cube. So that is Q23S. So, this expression gives us the distribution of shear flow in web 2, 3. Let us number it as 5. Now, if I have the cross section, I have already drawn the distribution for 1, 2. So, if I draw it for 2, 3, this is going to be given as, so this is 1, this is 2, this is 3 and this is 4. So, this equation is given by equation 5. The expression for this is given as equation 5. And we can, from this expression, we can find that Q3 is going to be Q23 into of H, if I put S equals to H, and that again if we calculate is going to be 0.42 SY by H cube. So, this also is 0.42 SY by H cube, okay, which is correct, which I can say it is correct because this has to be equal to Q2 because of the antisymmetry present in the cross section. Because the cross section is antisymmetric, Q3 has to be equal to Q2, and that has been proved from the solution of the problem as well. Now, for flange 3-4, we can as well use the same method that we have used, saying that S lies between H by 2 to 0 and Y is equal to H by 2 and X is equal to X is equal to S. When S is equal to 0, X is 0 and so on. So, if we substitute this into the expression that Qs minus Q0 is equal to Sy by H cube into 0 to S 10.32 X minus 6.84 Y into ds. We can as well find out Q, so this Qs is Q34S and Q0 is Q3. We can find out in this way, but also we can use the antisymmetry property of the cross section and can directly say that the distribution of shear flow in portion 3-4 is going to be just like this, that of Q12. So, this can be directly said. If I draw the direction of the shear flow, the first portion has shear flow in this direction, the second portion has shear flow in this direction, this one in this direction and this one. So, either I can find out in a long way by solving all this equation for portion 3/4, or we can use the antisymmetric condition and find out the shear flow distribution in the flange 3/4. So, this is the general methodology to find out the shear flow distribution in a thin walled open cross section. Thank you.